Now I want to look at how we can use kinetic molecular theory to explain what? Expansion. So how the subtopic kinetic molecular theory explanation of expansion. According to kinetic molecular theory of matter, when an object, e.g. solid, is heated, the molecules acquire kinetic energy, which enables them to overcome their intermolecular force. There are forces that hold molecules of solid together, very strong force. So whenever you now apply heat energy to solids, it helps the molecules of that solid to acquire energy, precisely heat energy there, yes, and it will now make them to now start moving. And once they are moving, when I say that they have now gained what? Kinetic energy. That heat energy has now been transformed or converted to what? Kinetic energy. And as they have acquired it now, it helps, it will not make them to do what? To vibrate in their mean what? Position, or in their fixed positions. We say thus the vibrations of the molecules increases because you are adding heat to the solids. And their displacement about their mean positions increase. As a result of this, the average distance between the molecules of the substance become larger, and this leads to an increase in the size of the substance. Are you getting it? And so as you now apply heat and they now vibrate in their mean position, the distance between the molecules will be what? Increasing. And so this brings about now enlargement in the size of the what? Molecules. And this leads to expansion of what? Solids. Now, experimental proof of expansion in solids. How can we use an experiment to demonstrate this? This can be demonstrated by using ball and ring experiments. This is known as this is the ring, this is the ball. The chain holds in the ball. Now let us look at the steps taken for this to be done. In carrying out this experiment, the following steps are taken. Number one, the metal ball is allowed to pass freely through the metal ring. You have this is the metal ring. Now this metal ball is allowed to pass through it freely. Are you getting it? When you have not heated the ball. So you have the metal ball is allowed to pass freely through the metal ring. Number two, the metal ball is strongly heated. The ball now is strongly heated and placed over the metal ring again. Remember, we said that when we apply heat to some solids, what happens? The molecules, they will vibrate about in their mean position. And once they vibrate about in their mean position, their positions will be what? The distance between the positions will be what? Increased, separated. And so it leads to expansion of the molecules of that solid. Now the metal ball is strongly heated and placed over the metal ring. What happens next? It is observed that the ball does not fit into the ring anymore because it has expanded. Are you getting it? And it has not expanded, so it cannot fit into the ring again. So the hot ball is allowed to cool sufficiently and placed over the ring again. Finally, it is observed that this ball now passes through the ring. Are you getting it? So look at the ball here, this side. First of all, you allow it to pass through, and then you heat it sufficiently. You heat it very well, that this will expand. And once it expands, it cannot pass through this ring again. And then allow it to cool again. It has now cooled sufficiently. Then try it again. What we have observed here is that the ball passed through the ring. This shows that application of heat to metal ball increases its size, and vice versa, the opposite. You can still use what we call compound bar experiments to explain the expansion of solids. We have hit a compound bar made of stripes of copper and iron, riveted together, placed together. Look at this. You have copper and iron of the same length at room temperature, called the bimetallic strip. So have at room temperature, the lengths are at the same here. Now you have it that there is no increase in temperature. there will not be change in what? In the length. Now there's change in temperature because we have added heat to it. You see that the copper now expanded more than that of what? Iron. Are you getting it now? And then it now bends with the one that has a more expansion than the other. We say heat a compound bar made of strips of copper and iron riveted together. The bar curves with metal, which expands most on the outside of the word curve. You see, the one that expands most is one that curves outwardly. Are you getting it? So this also shows another experiment to show expansion of what? Solids. Now we'll look at the next subtopic, expansivity. We'll have the first one is known as linear expansivity. On expansivity, I have said it today that an object can expand in length, and now we'll call it linear expansion. Now we'll have it in both length and breadth, that is area. We'll have it as well superficial expansivity, and then you'll have the other one as cubic, meaning when the length, breadth, and volume increase. We'll have that as what? Volume expansivity. Now, when we look at linear expansivity, linear expansivity of a solid is defined as the increase in length. Increase what? In length, per unit length, per degree rise in temperature. If you add heat to a solid object, we'll have it that there will be expansion. Now, we're not talking about increase in the length as a result of a degree rise in temperature of that. It has increased by 1 unit of the length. As a result of increase in 1 unit of the words, temperature, we have it known as linear expansivity. Are you getting it? For instance, you have a bar of 10 cm divided into 10 partitions. Each is 1 cm, right? Now, if you now add a unit, if you now add a degree rise in temperature, for instance, at the initial time, it was at, say, 10 degrees Celsius. And you now add 1 degree, you now increase the temperature by a degree rise in temperature. That brought about a unit change in the length of this bar. We call it linear what? Expansivity. So is the increase in length per unit length per degree rise in what? Temperature. Are you getting it? Now, from this, we'll have this mathematically represented as, we use this symbol alpha to be increase in length over original length times rise in what? Temperature. And increase in length here means expansion produced by the what? Solid. But the original length of that solid times rise in what? Temperature. Now, expansion now here gives you, how do you get the expansion produced? It's by gotten by final length of that object. Now, when you have added heat to it, there is no increase in temperature. Final length minus original length gives you the increase in length or the expansion produced over the original length of that metal times rise in what? Temperature. Now, from here we have x2 is the final length minus x1 is the original length over L1 original length also into theta 2 minus theta 1. So our theta 2 here, final temperature, our theta 1 is what? Initial temperature. So we can have it in some text. You can have x2 minus x1 over L1 into theta 2 minus theta 1, meaning expansion over original length over change in what? Temperature. We can still say L2 minus L1 means change in length over original length into theta 2 minus what? Theta 1. Are you following it? Where x2 minus x1 equal the expansion produced by the solid. x2 minus x1 is equal to the expansion produced by the what? Solid. The L2 means final length of the object when you must have added heat to it. Now L1 is initial length when you have not added heat to that object or the metal. Now theta 2 means final temperature, and theta 1 means initial temperature when you have not added heat to it. Theta 2 means the final temperature when you have added what? Heat. Is that okay? Now theta 2 minus theta 1 gives you change in temperature. Means the final temperature minus what? The original or initial temperature gives you what? Change in temperature. And from the equation, we'll have it that alpha is equal to L2 minus L1 over L1 into theta 2 minus this. From this equation, we want to get our L2, mean the final length. In case you're asked to get final length, how do you get the formula to solve that? Is that okay? So if you cross multiply here, you have L2 minus L1 is equal to alpha into L1 theta 2 minus what? Theta 1. Are you getting it? Remember, theta 2 minus theta 1 is change in theta. And so we have alpha L1 change in what? Theta, delta theta. And so we have L2 now give you alpha L1 change in theta. This is minus 1. Crossing over the equality sign becomes what? Plus. Is that okay? That becomes plus L1. Since L1 is common on the right-hand side of this equation, you have L1, you have L1. It is common. So you pick one of them as a common factor. So you have L2 is equal to L1 into, what is now remaining is alpha change in theta plus 1, because L1 times 1 is L1 here. L1 into this gives you alpha L1 change in theta, which is what you have here. L1 into 1 times 1 gives you what? L1. So I've now taken the common factor out. To factorize, we'll have L2 is equal to L1 into alpha change in theta plus 1. Or we can rewrite it to have L2 is equal to L1. This one now coming up first before the other one, you have 1 plus alpha change in what? Theta. Is that okay? So we can use this formula to get the final length gotten when the temperature increased by 1 degree rise in what? Temperature. So the SI unit of alpha is per Kelvin or per degree Celsius. So what we have is as the SI unit of what? Linear expansivity. It's given as per Kelvin or per degree Celsius. Note that the statement that the linear expansivity of a copper is 0.000017 per Kelvin or 0.00017 per degree Celsius means that a unit length of copper expands by 0.000017 units when its temperature rises by 1 Kelvin or 1 degree Celsius respectively. So sometimes they may ask you, what does it mean by the statement that the linear expansivity of copper is this? I get it. It means that the copper itself, it means that a unit of copper itself expands by this unit. Are you getting it? It means that a unit length of copper expands by this value, this unit, when a temperature of 1 Kelvin or 1 degree Celsius is added to it. You understand the point? So we have this noted. I want to look at experimental determination of linear expansivity of a brass. Here is the experiment. Here is the apparatus we use in determining this. We have this as a thermometer inside. We have this as a jacket covering the brass rods. I get it. Here is where the steam is gotten. Now the steam inlet, and then steam going out. As we go ahead, we will know what this apparatus is all about. The apparatus is set up as in the diagram above. The length L1 of the rod is first measured with a meter rule. The length of this rod first measure with what? Meter rule to know the original length of this rod, the brass rod there. The rod is then inserted into the steam jacket. Now after measuring it, you now insert this rod into the what? Steam jacket. One end of the metal rod is fixed firmly. Now look at the one that is fixed firmly. You have this end fixed what? Firmly. And the other end lies just outside the steam jacket and is free to move. It is free to do what? Move. The initial temperature of the rod is taken with the help or the edge of a thermometer. So before putting the steam, here you measure the initial temperature of this what? Rod with the help of what? A thermometer, which is inserted into the steam jacket. The micrometer screw gauge is screwed up till it just touches the free end of the rod. Here is the free end of this rod. Here is the fixed end of this rod. Now we say that this is the micrometer screw gauge. It is now screwed so as to touch the free end of this what? Rod. And the reading of the screw gauge is taken as what? X1. Now you now use that to measure the thickness of that. It is unscrewed from the free end and the steam is passed through the jacket for several minutes and the rod expands as a result of this heating. Now you have it that this micrometer screw gauge is used to measure the thickness of this, and then you have the steam pass through it. Now what is now the result of this? We have it that it is unscrewed from the free end and the steam is passed through the jacket for several minutes and the rod expands. So as you now pass the steam, the hot water, the steam now from it now, you have it that the rod expands as a result of this what? Heating. Now the gauge is screwed up again to make contact with the free end of the rod, and the new rating X2 is what? Noted. As heat is passed through the end or the free end of that rod, it will do what? Expand. And then the reading now is taken as what? X2. Now the steam temperature is also recorded as theta 2. Remember we have measured already with temperature, the initial temperature of the rod. Now, after now passing the steam through it now, you still measure the steam temperature and record it as what? Theta 2. Differences in the micrometer reading X1 minus X2 gives the expansion of the what? The rod. Now from here, how do you now calculate your linear expansivity? The expansivity alpha of the rod is calculated as follows. You have alpha is equal to change in length over original length times what? Temperature rise, which you have as L2 minus L1 over L1 theta minus what? Theta 2 minus theta 1. Or we can say expansion produced, which is X2 minus X1 over original length times rise in what? Temperature. I hope you are getting it. So here is the expansion now we have produced, which is now X2 minus what? X1 over the original length, which we have measured with the ruler there, times rise in temperature, which is final temperature of the steam minus original temperature of the what? Steam. Now I want to see how we can apply these formulas in solving some problems. Example 1. A rod of length 800 millimeters is found to expand 1.36 millimeters when heated from 15 degrees Celsius to 100 degrees Celsius. Calculate the value of the linear expansivity. So look at this rod here, a rod of length. Original length is 800 millimeters. Now it expanded by 1.36 millimeters. I get this expansion there. Now when heated from initial temperature is 15 degrees Celsius and final temperature theta 2 is 100 degrees Celsius. Now you have to calculate the value of the linear expansivity. So we're using alpha. We don't know what alpha. We want to use the formula alpha is equal to L2 minus L1 over L1 change in theta minus what? Theta 1. Or this formula can be written as expansion over L1 into theta 2 minus what? Theta 1. Already we have been given the value of expansion here to be 1.36. Is that okay? The original length is 800. Final temperature is 100 degrees Celsius. And initial temperature is what? 15 degrees Celsius. So now we have 1.36 over 800. 100 minus 15 gives you what? 85. So we have 1.36 over 68,000 because 800 times 85 gives you 68 what? Thousand. So 1.36 divided by 68,000 gives you 2 times 10 raised to the power minus 5 degrees Celsius. We can have it to be 0.00002 per degree what? Celsius. I think it's clear to you. Example 2. A copper rod whose length at 30 degrees Celsius is 10 cm. That's the initial length. Initial temperature is this. It's heated to 50 degrees Celsius. So final temperature is 50 degrees Celsius, theta 2. Find its new length. Find its what? New length. Take alpha for copper as 0.000017 per what? Kelvin. That's the SI unit of linear expansivity. So as I've said, initial length is 10 cm. Original temperature or initial temperature is 30 degrees Celsius. Final temperature is 50 degrees Celsius. What is the final length? Is that okay? Well, we'll have the linear expansivity of copper to be 0.000017 per degree Celsius. So how do you get your alpha? Alpha is L2 minus L1 over L1 into theta 2 minus what? Theta 1. So we want to substitute these values into this now and get our value. Now using L2 equal to L1 into 1 plus alpha change in theta. We've derived this formula today. Because a question like this will surely come up. So we'll have this that L2 is equal to 10 is initial length into 1 plus 0.00000. This is alpha now. Change in theta gives you 50 minus 30. So we have 50 minus 30 gives you 20 here. Bringing down this, plus we have 1. 10 is here. So we'll have the whole of this multiplied by 20 gives you 3.4 times 10 to the power minus 4 plus 1 gives you 1.00034. Now times 10 gives you 10.0034 cm. That gives you the final length. Is that okay? Now I want to look at the next one, known as area or superficial expansivity. I've told you that you're talking about change in both length and breadth. You're not talking about the area expansivity. Are you getting it? So how do we define this? We use beta to represent this as symbol. Beta to represent area or superficial expansivity. Unlike that of linear expansivity, whereby we use alpha. Now, this is the increase in area. Increase in what? Area per unit area. Per unit rise in temperature of a solid. You have an object that has both length and breadth. Now increase in both the length and the breadth. You understand? Per unit of it. As it is increasing in length, there is also increase in what? The breadth by 1 unit. Now as a result of change in temperature, ordinary 1 degree rise in what? Temperature. Could be in degrees Celsius or in Kelvin. Only by rise in per unit rise in what? Temperature. So a result of rise as a result of unit rise in what? Temperature. Brings about here increase in the area of that object. Per unit area of that object, what brings about that is rise in what? Temperature. So we say it is given by the formula change in area over original area times rise in what? Temperature. That gives you the formula of area expansivity. From that, we'll have it to be A2 minus A1. That is change in area, or change in what? Area. Final area minus original area over A1, which is the initial area, change in what? Temperature. Theta 2 minus theta 1. Final temperature minus initial what? Temperature. And so beta here gives you A2 minus A1 all over A1 change in what? Theta. And from the equation, A2 minus A1 is equal to, because multiply here, you have A2 minus A1 give you beta into A1 change in what? Theta. So A2 now will give you beta A1 change in theta. This is minus A1 crossing over now because what? Plus A1. This is how we'll have this here. So A2 is equal to A1 into beta change in theta plus 1 because A1 is common here. There are two here, so you take only one of them. Or you can still write this to be A2 equal to A1 into 1 plus beta change in what? Theta. So where our A1 is area of the object at the initial temperature. We have not added heat. Now A2 is the area of the object at theta 2. When you have added what? Heat. Which leads now to increase in what? Temperature. I will have this at the delta theta to be changed in what? Temperature, which is theta 2 minus what? Theta 1.